Hello my friends. In this video, we will learn about how the train works, specifically the electric locomotive. So, let's start our video. An electric locomotive is a locomotive powered by electricity from overhead lines, a third rail or onboard energy storage, such as a battery or a supercapacitor. Locomotives with onboard fueled prime movers, such as diesel engines or gas turbines, are classed as diesel-electric or gas turbine-electric, and not as electric locomotives because the electric generator and motor combination serves only as a power transmission system. Electric locomotives benefit from the high efficiency of electric motors, often above 90%, not including the inefficiency of generating the electricity. Additional efficiency can be gained from regenerative braking, which allows kinetic energy to be recovered during braking to put power back on the line. Newer electric locomotives use AC motor inverter drive systems that provide for regenerative braking. Electric locomotives are quiet compared to diesel locomotives since there is no engine and exhaust noise and less mechanical noise. The lack of reciprocating parts means electric locomotives are easier on the track, reducing track maintenance. Power plant capacity is far greater than any individual locomotive uses, so electric locomotives can have a higher power output than diesel locomotives, and they can produce even higher short-term surge power for fast acceleration. Electric locomotives are ideal for commuter rail service with frequent stops. Electric locomotives are used on freight routes with consistently high traffic volumes or in areas with advanced rail networks. Power plants, even if they burn fossil fuels, are far cleaner than mobile sources such as locomotive engines. The power can also come from low-carbon or renewable sources, including geothermal power, hydroelectric power, biomass, solar power, nuclear power, and wind turbines. Electric locomotives usually cost 20% less than diesel locomotives. Their maintenance costs are 25 to 35% lower and cost up to 50% less to run. The chief disadvantage of electrification is the high cost for infrastructure overhead lines or third rail, substations, and control systems. The impact of this is different depending on local laws and regulations. For example, public policy in the US interferes with electrification. Higher property taxes are imposed on privately owned rail facilities if they are electrified. The EPA regulates exhaust emissions on locomotive and marine engines, similar to regulations on car and freight truck emissions, in order to limit the amount of carbon monoxide, unburnt hydrocarbons, nitric oxides, and soot output from these mobile power sources. Because railroad infrastructure is privately owned in the US, railroads are unwilling to make the necessary investments for electrification. In Europe and elsewhere, railway networks are considered part of the national transport infrastructure, just like roads, highways, and waterways, so are often financed by the state. Operators of the rolling stock pay fees according to rail use. This makes possible the large investments required for the technically and, in the long term, also economically advantageous electrification. The first practical AC electric locomotive was designed by Charles Brown, then working for Oerlikon Zurich. In 1891, Brown had demonstrated long-distance power transmission for the International Electrotechnical Exhibition using three-phase AC between a hydroelectric plant at Laufen am Neckar and the expo site at Frankfurt am Main West, a distance of 280 kilometers. Using experience he had gained while working for John Heilmann on steam electric locomotive designs, Brown observed that three-phase motors had a higher power-to-weight ratio than DC motors, and, because of the absence of a commutator, were simpler to manufacture and maintain. However, they were much larger than the DC motors of the time and could not be mounted in underfloor bogies. They could only be carried within locomotive bodies. In 1896, Oerlikon installed the first commercial example of the system on the Lugano tramway. Each 30-ton locomotive had two 110 kVA, 150 HP motors run by three-phase 750 V40 Hz, fed from double overhead lines. Three-phase motors run at a constant speed and provide regenerative braking and are thus well suited to steeply graded routes. In 1899, Brown, by then in partnership with Walter Boveri, supplied the first mainline three-phase locomotives to the 40-kilometer Burgdorf-Thun Railway. highest point 770 meters, Switzerland. The first implementation of industrial frequency single-phase AC supply for locomotives came from Oerlikon in 1901, using the designs of Hans Behn-Eschenberg and Emil Huber Stocker. Installation on the Seebach-Wettingen line of the Swiss Federal Railways was completed in 1904. The 15 kV, 50 heads 345 kilowatt, 460 HP, 48-ton locomotives used transformers and rotary converters to power DC traction motors. In 1894, Hungarian engineer Kalman Kando developed a new type of three-phase asynchronous electric drive motors and generators for electric locomotives at the Fives Lille Company. Kando's early 1894 designs were first applied in a short three-phase AC tramway in Évian-les-Bains, France, which was constructed between 1896 and 1898. In 1918, Kando invented and developed the rotary phase converter, enabling electric locomotives to use three-phase motors while being supplied via a single overhead wire, carrying the simple industrial frequency, 50 Hz, single-phase AC of the high-voltage national networks. Italian railways were the first in the world to introduce electric traction for the entire length of a main line rather than just a short stretch. The 106-kilometer Valtellina line was opened on September 4, 1902, designed by Kando and a team from the Gans works. The electrical system was three-phase at 3 kilovolts, 15 Hz. The voltage was significantly higher than used earlier, and it required new designs for electric motors and switching devices. The three-phase two-wire system was used on several railways in northern Italy and became known as the Italian system. Kando was invited in 1905 to undertake the management of Società Italiana Westinghouse and led the development of several Italian electric locomotives. During the period of electrification of the Italian railways, tests were made as to which type of power to use. In some sections, there was a 3,600 volt, 16 2/3 Hz three-phase power supply. In others, there was 1,500 volt DC, 3 kilovolt DC, and 10 kilovolt AC, 45 Hz supply. After World War II, 3 kilovolt DC power was chosen for the entire Italian railway system. In Europe, electrification projects initially focused on mountainous regions for several reasons. Coal supplies were difficult, hydroelectric power was readily available, and electric locomotives provided more traction on steeper lines. This was particularly applicable in Switzerland, where almost all lines are electrified. An important contribution to the wider adoption of AC traction came from SNCF of France after World War II. The company had assessed the industrial frequency AC line routed through the steep Höllental Valley in Germany, which was under French administration following the war. After trials, the company decided that the performance of AC locomotives was sufficiently developed to allow all its future installations, regardless of terrain, to be of this standard, with its associated cheaper and more efficient infrastructure. The SNCF decision, ignoring as it did the 2,000 miles of high-voltage DC already installed on French routes, was influential in the standard selected for other countries in Europe. An electric locomotive can be supplied with power from rechargeable energy storage systems, such as a battery or ultracapacitor-powered mining locomotives. It can also be supplied from a stationary source, such as a third rail or overhead wire. The distinguishing design features of electric locomotives are the type of electrical power used, AC or DC, the method of storing, like batteries or ultracapacitors, or collecting, like transmission, electrical power, and the means used to couple the traction motors to the driving wheels or drivers. Direct and alternating current. The most fundamental difference lies in the choice of AC or DC. The earliest systems used DC, as AC was not well understood, and insulation material for high-voltage lines was not available. DC locomotives typically run at relatively low voltage, between 600 to 3,000 volts. The equipment is therefore relatively massive because the currents involved are large in order to transmit sufficient power. Power must be supplied at frequent intervals, as the high currents result in large transmission system losses. As AC motors were developed, they became the predominant type, particularly on longer routes. High voltages in the tens of thousands of volts are used because this allows the use of low currents. Transmission losses are proportional to the square of the current. For example, twice the current means 4 times the loss. Thus, high power can be conducted over long distances on lighter and cheaper wires. Transformers in the locomotives transform this power to a low voltage and high current for the motors. A similar high voltage, low current system could not be employed with direct current locomotives because there is no easy way to do the voltage and current transformation for DC as efficiently as achieved by AC transformers. AC traction still occasionally uses dual overhead wires instead of single-phase lines. The resulting three-phase current drives induction motors, which do not have sensitive commutators and permit easy realization of a regenerative brake. Speed is controlled by changing the number of pole pairs in the stator circuit, with acceleration controlled by switching additional resistors in or out of the rotor circuit. The two-phase lines are heavy and complicated near switches, where the phases have to cross each other. The system was widely used in northern Italy until 1976 and is still in use on some Swiss rack railways. The simple feasibility of a fail-safe electric brake is an advantage of the system, while speed control and the two-phase lines are problematic. Rectifier locomotives, which used AC power transmission and DC motors, were common, though DC commutators had problems both in starting and at low velocities. Today's advanced electric locomotives use brushless three-phase AC induction motors. These polyphase machines are powered from GTO, IGCT or IGBT-based inverters. The cost of electronic devices in a modern locomotive can be up to 50% of the cost of the vehicle. Electric traction allows the use of regenerative braking, in which the motors are used as brakes and become generators that transform the motion of the train into electrical power that is then fed back into the lines. This system is particularly advantageous in mountainous operations, as descending locomotives can produce a large portion of the power required for ascending trains. Most systems have a characteristic voltage and, in the case of AC power, a system frequency. Many locomotives have been equipped to handle multiple voltages and frequencies as systems came to overlap or were upgraded. American FL9 locomotives were equipped to handle power from two different electrical systems and could also operate as diesel electrics. While today's systems predominantly operate on AC, many DC systems are still in use. For example, in South Africa and the United Kingdom, 750 volts and 1500 volts. Netherlands, Japan, Ireland, 1500 volts. Slovenia, Belgium, Italy, Poland, Russia, Spain, 3000 volts, and Washington, D.C., 750 volts. Electrical circuits require two connections, or for three-phase AC, 3 connections. From the beginning, the track was used for one side of the circuit. Unlike model railroads, the track normally supplies only one side, the other side or sides of the circuit being provided separately. Overhead lines. Railways generally tend to prefer overhead lines, often called catenaries, after the support system used to hold the wire parallel to the ground. 3 collection methods are possible. Trolley pole, a long flexible pole which engages the line with a wheel or shoe. Bow collector, a frame that holds a long collecting rod against the wire. Pantograph, a hinged frame that holds the collecting shoes against the wire in a fixed geometry. Of the 3, the pantograph method is best suited for high-speed operation. Some locomotives use both overhead and third rail collection, like the British Rail Class 92. In Europe, the recommended geometry and shape of pantographs are defined by standard EN 5367 or IEC 6046. Third rail. Mass transit systems and suburban lines often use a third rail instead of overhead wire. It allows for smaller tunnels and lower clearance under bridges and has advantages for intensive traffic as it is a very sturdy system, not sensitive to snapping overhead wires. Some systems use 4 rails, especially some lines in the London Underground. One setback for third rail systems is that level crossings become more complex, usually requiring a gap section. The original Baltimore and Ohio Railroad electrification used a sliding pickup, a contact shoe, or simply the shoe, in an overhead channel, a system quickly found to be unsatisfactory. It was replaced by a third rail in which a pickup rides underneath or on top of a smaller rail parallel to the main track above ground level. There are multiple pickups on both sides of the locomotive in order to accommodate the brakes in the third rail required by track work. This system is preferred in subways because of the close clearances it affords. A battery electric locomotive, or battery locomotive, is powered by onboard batteries, a kind of battery electric vehicle. Such locomotives are used where a diesel or conventional electric locomotive would be unsuitable. An example is maintenance trains on electrified lines when the electricity supply is turned off. Another use for battery locomotives is in industrial facilities, like explosives factories, oil and gas refineries, or chemical factories, where a combustion-powered locomotive, whether steam or diesel-powered, could cause a safety issue due to the risks of fire, explosion, or fumes in a confined space. Battery locomotives are preferred for mine railways where gas could be ignited by trolley-powered units arcing at the collection shoes, or where electrical resistance could develop in the supply or return circuits, especially at rail joints, and allow dangerous current leakage into the ground. The first electric locomotive built in 1837 was a battery locomotive. It was built by chemist Robert Davidson of Aberdeen in Scotland, and it was powered by galvanic cells or batteries. Another early example was at the Kennecott copper mine in McCarthy, Alaska, where in 1917 the underground haulage ways were widened to enable working by two battery locomotives of 4.5 short tons. In 1928, Kennecott Copper ordered 4 700 series electric locomotives with onboard batteries. These locomotives weighed 85 short tons and operated on 750 volts overhead trolley wire with considerable further range whilst running on batteries. The locomotives provided several decades of service using nickel-iron battery or Edison technology. The batteries were replaced with lead-acid batteries and the locomotives were retired shortly afterward. All 4 locomotives were donated to museums, but one was scrapped. The others can be seen at the Boone and Scenic Valley Railroad in Iowa and at the Western Railway Museum in Rio Vista, California. Historically, Canada has used a variety of electric locomotives, primarily for moving passengers and cargo through poorly ventilated tunnels. Electric locomotives that were in use in Canada include the St. Clair Tunnel Company Boxcab Electric, CN Boxcab Electric, and GMD GF6C. EXO in Montreal operated ALP45DP dual-mode electro-diesel locomotives in order to allow the locomotives to traverse the poorly ventilated Mount Royal Tunnel. The locomotives run in electric mode along the entire length of the Deux Montagnes line and along the Mascouche line between Montreal Central Station and Ahuntsic Station. The locomotives run in diesel mode for the remainder of the Mascouche line and along 3 other non-electrified lines. However, with the conversion of the Mount Royal Tunnel into the main line of the Réseau Express Metropolitain Light Metro system and the permanent truncation of the Mascouche line to Ahuntsic Station starting in January 2020, the locomotives are run exclusively in diesel mode. Similar to the United States, the flexibility of diesel locomotives and the relatively low cost of their infrastructure has led them to prevail except where legal or operational constraints dictate the use of electricity. This has led to limited electric railway infrastructure and, by extension, electric locomotives operating in Canada today. As of 2021, only one example exists today. GMD SW200 MG electric locomotives operated by the Iron Ore Company of Canada for a small isolated railway hauling raw ore from their Carroll Lake mine to a processing plant. Thanks for watching this video. For more videos, do subscribe and share. Please comment.